Let's start with the rhetorical question. If electrons repel each other, shouldn't bonds repel each other too? Because they're made up of electrons. And the answer is absolutely. They should definitely be repelling each other, which is a really obvious and intuitive thing, right? But the results for it are not necessarily intuitive. So let's see what's going to happen when we start thinking about that. Well, what we're going to get is we're going to get a theory that's going to be called VSEPR, valence shell electron pair repulsion. And people have a bear of a time remembering that one. But what are we really talking about? Well, we're saying that all of the valence level electrons, the ones that we're talking about when we count to the octet, they're going to start repelling each other because, they're electrons. They have negative charges. Negative charges repel each other. And so, if we think about how many of these electron pairs there are in space, and we picture them all repelling each other, we're going to get 3D structures. When we think of the valence shell electron pairs repelling each other, we're going to have a pretty good idea of what things look like in 3 dimensions. That's what we're talking about when we unpack the crazy title that this thing's going to have. Now, there's the second theory that we're going to learn about, and it was actually developed at the same time, completely independently. This theory we're talking about here, VSEPR, focuses on where the electrons are and what that means for the shapes. The other theory thinks about where the electrons and neutrons are, and protons are, takes the nucleus and the protons within, the electrons zipping around them, and comes up with orbitals just like we would have done for atoms. But we get the same result either way. There's a little bit of extra nuance that comes in the other technique, but this one is much easier to understand, so we typically talk about VSEPR first. But keep in mind that both these theories are going to be telling us pretty much the same thing. Now, the book is going to talk about electron domains, and that really throws people a lot of the time. What we're talking about with an electron domain is that it's a region of space that has electrons, and we don't care how many electrons are in that region of space. So let me give an example. If I've got a proton right here, or a nucleus, whichever one you want to think of, this could be hydrogen or something like that, right? If we've got a bonding region right here, that's one region of space. Now, I'm not going to be looking at both atoms simultaneously. I'm going to focus on a central atom. So I'm going to pick one of the atoms and I'm going to look at it. When I zoom in to look at this one, all I'm going to see about it is that it's got electrons pointing off in this direction of space, right? So I'm going to say that's one region. Now, what if that was a double bond? It's one region. They're still pointing between it and the neighbor. How about the triple bond? Again, one region. Now I've just got 6 electrons that happen to be in this region between these 2 nuclei, but I don't care about how many electrons are there. All I care is that there's a pair of electrons or more in one region of space. Even a single electron would do it, in fact. If I had a radical, it would take up one region in space. That would be an electron domain. A lone pair would be an electron domain. These are all going to be electron domains, so don't let that throw you when we talk about domains. Don't care how many electrons are within the domain. We're just talking about the fact that it's a space in space with electrons in it. Now, because it has electrons in it, those domains are going to repel each other. And from that, we can get a good idea of what the 3-dimensional picture should look like. Let me give you an example. Suppose that I've got 3 domains. They could be 2 single bonds and a double bond. It could be a triple bond and 2 single bonds. It could be 2 electron pairs and a double bond. Who cares? As long as we have 3 domains, right? Well, how can I space these out so that they're repelling each other the best that I can? I can make them shape like a triangle sitting along a plane. Now look, if I bend it like this, my orange highlighter just got closer to the other pens, right? They're going to repel it back forward. So, it's going to be back into the plane. How about if I squeeze them like this? They're getting closer together. They're going to be pushed right back out. And so we expect that if we have 3 domains, it's going to end up sitting in a plane and being shaped like a triangle. That's the magic thinking that lies behind VSEPR. It's not actually that complicated if we approach it like that. The notation for it and the names for it can get overwhelming if we let them, but they shouldn't. It's all predicated on that idea and then keeping track of things from there. Now, the number of electron groups are going to determine the shape of the molecule, like we just saw. And it's going to be the first time that we can get things into 3 dimensions. Now, here's the other thing I want us to understand, is that if we're doing a big molecule, we're going to be going through and talking about each atom the central atom separately, because we can have different geometries at different spots in a big molecule. If you need to picture one like that, picture something like DNA. You probably have seen a picture of DNA before. You might have even seen spots in it that had double bonds and that are going to be flat, that are very small, of course. And then you're going to have lots of single bonds where you can twist things around and it has these angles. That's the kind of thing we're talking about. It's a bit like building with Legos or Tinker Toys or something. That's what's going to be the cornerstone for VSEPR. So let's go ahead and take a look at how these are all going to be arranged in space and see how the different number of electron groups we've got, electron regions, electron domains, whatever way you want to say it, are going to end up filling space and repelling the others.